On behalf of the Granger College of Engineering, let me say that we're extremely proud of Charles and his accomplishment. This recognition is definitely a major milestone in Charles' career, but just like many milestones mark distances along roadways, we anticipate that this will only be one of the many milestones in his career. We're all looking forward to many more contributions to his field, to the research, teaching, and service missions of the department, the college, and this university. Named faculty positions communicate the global eminence of our faculty to the world academic community. They empower us to open new worlds of discovery through brilliant scholarship and to make an impact on humanity. They are critical in the retention of world-class scholars like Charles Gammie, and that we have here at the University of Illinois. So today begins a new day for Charles, one that encompasses and anticipates the yet unknown breakthrough knowledge and pioneering research made possible to the support of generous donors like the Willett family. So today is a day to celebrate excellence, excellence in teaching, excellence in research, excellence in service. So, Professor Gammie, will you please come forward to receive the medal? First thing we always do is check to see the right name. Push on the box. Yeah. Thank you very much. Oops. There. Sorry. There.
Engineering professor.
Not rocket science, but. All right. So.
My turn. So let me see if I can put this together. All right. Well, thank you all for coming today, and a special thank you to Gil for his remarks. It's both interesting and a pleasure to be your colleague. Much appreciated. It's also terrific to have this event in this lecture hall, where I've spent much of my teaching career. So this deep seating really intimidated me when I was an assistant professor, as I'm sure many of you remember when you started. And it always reminded me of a medical lecture hall, and I'll leave it to your imagination as to who exactly is playing what role in this picture. So I always think of this painting by Eakins when I walk in. I have many people to thank for enabling me to be here today. Far too many for the time available. But first, I have to thank my family, my father, my mother, and my brother. My father was a Scottish radio engineer, and after World War II, he came to the United States, where he became a member of technical staff at Bell Labs, and met my mother, who is an artist working in advertising. If you made a long-distance call in the 1970s, you used his work. As my father spent his evenings working at our dining room table, he also taught me to program on a Bell Labs issued HP 65 calculator. And that is more or less what I am still doing today. He would be pleased and not a little bit surprised to see his son become a chair professor of engineering. So for my mother, I learned persistence and the joy of reading and writing. And for my brother, I learned to fight back. He was a real pain in the neck. And he is now my second most trusted source of advice, and cardiac surgeon-in-chief at Johns Hopkins. My most trusted source of advice, and the one to whom I owe the greatest debt, is my wife, Kristen Hoganson. Were it not for her suggestion that I consider graduate school, my undergraduate trajectory toward law school would have continued uninterrupted, and with who knows what consequences. She has managed somehow to do more than half the parenting for our 3 very active children, and put up with me, while at the same time advising the State Department, and she can't tell me exactly what she's advising them about, writing 3 significant books and editing a few more, and being the Stroop Professor of American History. I also owe a great debt to my children. Our 2 older children, Jerry and Annie, live too far away now to be with us. Jerry seems destined to be a computer scientist, and Annie seems destined to be in mathematics. But our youngest child, Edie, who, thank goodness, is now able to walk again after running a half marathon over the weekend, is here. So from my children, I hear about the much prepared for meetings with thesis advisors. And I sense the impact of a beautiful proof in number theory on an impressionable young mind. And I am constantly reminded of the sheer energy, excitement, and impatience that goes with being a teenager. So it is through their eyes and ears and texts that I have an inkling of what it means to be a student in 2022. Also, like all academics, like all of us, I owe a great debt to my mentors. And there were many, many over the years, so we would be here all afternoon with a list of my mentors. But one in particular I want to mention. My postdoctoral sponsor at the University of Virginia was John Hall, who has recently passed away. And John was an Illinois PhD and a student of NCSA founder Larry Smar. And his thinking had a profound effect on me, especially his confidence that it was possible to use computers to discover new things about the universe. I also owe so much to my colleagues here at Illinois and to the staff in my 2 departments. My department EOs have been unstintingly supportive, especially Matthias Gross-Perdekamp and Leslie Mooney, who's over here. And before them, Brian Fields and Dale Van Harlinger. I remember with special gratitude Jeremiah Sullivan, who many of you knew. So he would drop by my office, sit down, ask me what I was working on, and he would listen to what I was doing and engage with it. And he told me he was there if I ever needed support. And I remember thinking that this guy is really in my corner. Nowadays, I'm especially happy to have so many active and brilliant colleagues to talk to, many of whom are here. And I have particularly benefited from our new Illinois Center for the Advanced Study of the Universe, or ICASU, that brings together researchers from across fundamental physics under the energetic leadership of Nico Yunus, who has been laid low today by a Belgian baguette, I understand. Finally, I would like to thank my students and postdocs. So can you guys stand up just for a second? They are the people who keep me going scientifically. I've supervised, thank you. So I've supervised 33 undergraduate research students, 21 graduate students, and 4 postdocs while here. And my students and postdocs constantly challenge me, teach me new things, and make me a better teacher and researcher. Thank you, all of you. I learned all my best Python tricks from you. Now I'd like to say a few words about part of what my group and I do and look to the future. So I'm going to start with this beautiful picture from the Hubble Space Telescope, which shows a galaxy, which is a collection of billions of stars orbiting around one another, a galaxy called M87. And you'll notice that there's a bright line coming out of the very center. It was first noticed by an American astronomer named Heber Curtis more than 100 years ago. So that bright line is called a jet, and it's made of hot gas emerging from the center of the galaxy at close to the speed of light. So jets can be seen in radio waves, they can be seen in infrared and visible light, and in gamma rays. And they're common, they're as big as galaxies, and they can be seen from across the universe. So in the 1970s, two astrophysicists working at Cambridge in the UK, Roger Blanford and Roman Znayak, had an inspiring idea about the origin of jets. So they argued that at the base of each jet, in the center of the galaxy, there's a black hole. And the black hole is spinning and acts as a giant flywheel, storing vast amounts of energy. So Blanford and Znayak showed that you could use magnetic fields that could thread the black hole and be dragged by the hole's rotation to tap that spin energy and to provide more power that is radiated by a billion suns. So this, in my opinion, is one of the great ideas in astrophysics. It brings together gravitational physics, plasma physics, and astronomy. And it tells us something new about the universe, that these large, bright, easily detectable jets are announcing the existence of a black hole, of a spinning black hole at their base. And if Blanford and Znayak are correct, these jets signal the truth of one of the most surprising ideas in gravitational physics, which is that it is possible to get energy out of a black hole, to get something out of nothing. And this is truly a beautiful theory. So in physics, however, experiment sits as the ultimate judge of theory. And to paraphrase Benjamin Franklin, a beautiful theory is often murdered by a gang of ugly facts. So how can we test this beautiful theory experimentally? So a starting point was to ask whether there is actually a black hole at the base of M87's jet. And this is something that people worked on for decades. But until recently, all of the evidence for that was quite indirect. And over the last 5 years, my group and I have been working with an international team of scientists called the Event Horizon Telescope Collaboration, which was formed with the goal of taking a picture of the black hole in M87. So Event Horizon Telescope is not a single telescope, but a network of high-frequency antennas, radio antennas, distributed around the globe. And it can take pictures of unprecedented clarity by combining the signals detected at widely separated antennas and using a technique known as very long baseline interferometry, or VLBI. And this technique was pioneered by the late George Svensson, who was an Illinois professor of electrical engineering. George literally wrote the book on VLBI. So the anchor site for the Event Horizon Telescope Network is called ALMA, which is a billion-dollar observatory located in the Atacama Desert of northern Chile. And this video will show you what you see as you look upwards from ALMA toward M87. And so this is going to zoom in on the galaxy and the jet through a composite of observations at different wavelengths, and finally finishes with the Event Horizon Telescope image of the black hole that sits at the base of the jet, which was unveiled in 2019. And as you'll see, as Blanford and Znayak anticipated and others anticipated, there's a black hole at the base of the jet. And the black hole here is that gap in the middle, which is known as the shadow of the black hole. And the light that you're seeing is not from the hole itself, but from hot gas around the black hole. So what my students, postdocs, and I do is predict what the Event Horizon Telescope will see in the future and provide a physical interpretation for what's already been observed. And to do this, we build computational models of the black hole and surrounding gas and run them on the largest available supercomputers. So this enables us to see our models of black holes with even higher resolution than is possible with Event Horizon Telescope, and even to make a movie of gas falling into the black hole. So we found that M87 looked just about exactly the way we expected to. And this was a real triumph, I think, for computational astrophysics. And interestingly, all of our models were consistent with a rotating black hole, as Blanford and Snayak would have predicted. So M87 is not the only black hole that Event Horizon Telescope can see. It can also see the black hole that's at the center of our galaxy. So to orient you, here's an image of the entire sky as seen at wavelengths visible to the human eye. And you can see that the sky is, or my pointer, but you can see that the sky here is dominated by the Milky Way. So this image is oriented with the center of the galaxy at the very center, and the galaxy oriented along the galactic equator. So this galaxy, our galaxy, is disk-shaped and looks quite different from M87, partly because we're sitting inside the disk. And at the very center is a black hole that is much, much smaller than M87. But it's much closer to us than M87. And so it has the same apparent size on the sky. So it's a trick of perspective that it looks the same size. And studies of stellar orbits around this black hole won Reinhard Genzel and Andrea Ghez the Nobel Prize in Physics in 2020. So Event Horizon Telescope has looked at this black hole several times, and we've been working really hard over the last 18 months to build computational models. And we produced lots of them. So here's a library of simulations produced by my group that we have compared to the Event Horizon Telescope's Galactic Center observations. I would very much like to be able to share with you what we learned by comparing these models with the observations, but the results are embargoed until next week, when on May 12th, they'll be unveiled at a press conference, simultaneous press conference in Munich, Washington, D.C., Taipei, Santiago, and elsewhere. So stay tuned. So our work on the Galactic Center is now done. And my group and I are moving on to new challenges. And in particular, how can we probe EHT observations, Event Horizon Telescope observations, more deeply and construct better models and continue to run far, far ahead of the competition. So one way forward here is to move to larger computers. And my student Ben Prather recently led an effort to win a massive allocation of time on a machine called Summit. This is it, at Oak Ridge National Laboratory. This is the most powerful, publicly accessible supercomputer in the United States, and second most powerful in the world after Japan's Fugaku machine. So as we speak, I believe a set of Ben's next generation models are sitting in the queue, waiting to run on Summit. So a second way forward is to enhance the observational capabilities of the Event Horizon Telescope itself by placing one of its antennas in space. And to this end, we're working on a project called Saltus that proposes to launch a 23-meter diameter inflatable mirror into the orbit that is shown here. So I should explain, this orbit looks impossible to you. It is. This is in the rotating frame. And so we're seeing the orbit move back and forth from first quarter moon to third quarter moon, roughly. So the angular resolution of the LBI network is inversely proportional to the distance between its most widely separated antennas. And so this proposed mission would make it possible to resolve tens to hundreds more black holes, to resolve binary black holes at cosmological distances, and to measure the rotation of the black hole in M87 directly, which is another crucial step toward testing this Blanford and Snayak's beautiful theory, and to sensitively probe the gravitational field of M87's black hole and check that it is consistent with expectations from Einstein's theory of general relativity. So this program of research will be supported in part by funds provided by the Willett Chair. I've never been hesitant about taking intellectual risks, but the Willett Chair funds will enable my group and I to invest in a broader spectrum of really speculative, high-risk, high-reward projects. So let me close by again expressing gratitude to the University of Illinois, the college, the Granger College of Engineering and the Department of Physics, and the College of Liberal Arts and Sciences and the Department of Astronomy. So I'm honored to accept the Willett Chair, but really the greatest honor of my career has been to be part of such a supportive, interesting, and really distinguished community of scientists and engineers.